Hello everyone, welcome to lecture 1.2. We're going to introduce heterogeneous parallel computing. The main objective of this lecture is for students to learn the major differences between latency devices, which are CPU cores, and throughput devices, which are GPU cores. By understanding these differences, students would understand why winning applications increasingly use both types of devices. In a heterogeneous parallel computing system, we use different types of devices that best fit the particular part of the application in question. So here we show a simple example of the mobile system on chip today. We will typically have latency cores, which are CPU cores, and we will also have throughput device cores, which are GPU cores. Oftentimes, we have hardware IPs that would accelerate certain types of functionality, such as video processing. We also will have DSP cores that typically are used for baseband processing and communication. And we sometimes can find configurable logic and cores on these SoCs to accommodate special needs for applications. And of course, we will find on-chip memories in these chips. Even in the bigger picture, we oftentimes will find a trade-off between computing on these devices versus sending the application to cloud services. So throughout the entire software development process, a developer must consider the best fit of each type of computing resources in the big picture. So this slide shows that CPUs and GPUs are designed very differently. We're going to go over the details in the next few slides, but here we show pictorially what are the major differences so that we can have students to build a mental model for these differences. The first obvious difference should be the cache memory. We see that the CPU cores tend to have much bigger amount of cache memory. And the second difference is that we see that GPUs tend to have a bigger amount of combination of registers and SIMD units compared to the CPUs. And the third difference is that we see very substantial amount of control logic on the CPUs, whereas on the GPUs we tend to see more threading management logic. In this slide, we show a few features of CPUs that allow the CPUs to be latency-oriented devices. First of all, we show that they're fairly large ALUs, as shown as large green boxes, and these are powerful ALU designs that reduce arithmetic operation latency. And the second feature is fairly large amount of cache memory that are designed to convert low latency memory accesses to short latency cache accesses. This is done by reusing data in the cache so that the reused data can be accessed with much shorter latency. And the third one is sophisticated control logic in the yellow box. And these sophisticated control logic help to make branch prediction for reduced branch latency and to support data forwarding to reduce the latency between data production operations and the data consumption operations. Here we show a few features of GPUs that allow them to be throughput-oriented devices. We see that there's usually a small amount of cache memory that are used as boosting device mechanism for memory throughput, and we will show this in next few in several future lectures. And we also see that we have relatively small amount of control logic, and where usually no branch prediction or data forwarding are supported. But as a result of having smaller caches and simple control, the GPU chips tend to be able to accommodate a large number of small ALUs. And these ALUs have fairly long operation latency but are heavily pipelined for high throughput. So we have many high throughput arithmetic pipelines that are all capable of producing results at the same time. As a result, we can have a very large number of arithmetic operations going in parallel. However, in order to fully utilize this kind of capacity, the GPUs require massive number of threads in order to tolerate all these latencies and fully utilize all the parallel computing resources. That's why we're going to also see a large amount of thread logic and thread state in these GPUs. Now that we have seen that CPUs and GPUs are designed for very different strengths and weakness, then we should be able to easily understand why winning applications use both CPUs and GPUs. They will use CPUs for sequential parts where latency matters. And in typical parts of the application where there's very little parallelism, CPUs can be 10 times or more faster than GPUs for this sequential code. On the other hand, GPUs are very good with parallel parts where throughput wins. When you have so much parallelism in some of these applications, just being able to get many computations through, even though each computation may take a long latency, can be a very big win. In those situations, GPUs can be 10 times or more faster than CPUs. This slide shows that there are two volumes of GPU computing gems that contain about 90 articles. And these articles actually are case studies of how people use GPU in heterogeneous computing to achieve their application goals. And in these two volumes, you will find that there are many disciplines that are currently utilizing heterogeneous parallel computing. And these disciplines cover many of the high-value applications that we currently have in our society, including data-intensive compute analytics, and including biomedical informatics, including medical imaging, financial analysis, and so on. So I highly recommend that students who are interested in using heterogeneous parallel computing for their own applications to look into articles of interest in these volumes. Thank you.